What if, in the very first fleeting moments of existence, the entire universe expanded faster than the speed of light? Picture this: a newborn cosmos, smaller than a single atom, suddenly stretching to unimaginable scales in less time than it takes to blink. This wasn't just rapid growth, it was an eruption, a cosmic sprint so violent and mysterious that it defies everything we think we know about physics. Welcome to the cosmic inflation era, a split-second chapter in our universe's story where the rules seem to bend and reality itself played by a different script. Today, we're diving deep into 25 mind-bending mysteries from this enigmatic period, questions that still leave scientists wide-eyed and restless. How could space inflate like a balloon with no air? What hidden forces were at work, stretching the fabric of reality beyond comprehension? And most haunting of all, what clues did this explosive beginning leave behind, etched into the cosmos like cosmic fingerprints? The answers might rewrite not just our understanding of the Big Bang, but the very nature of existence. This isn't just a story about distant galaxies or abstract physics. It's about the origins of everything: the stars above us, the ground beneath our feet, even the atoms that make up your body. The cosmic inflation era set the stage for all of it, and yet it remains one of the greatest unsolved puzzles in science. So buckle up, we're about to journey back to the very edge of time, where the universe was wild, uncharted, and full of secrets waiting to be uncovered. Let's unravel them together. But what could have sparked this sudden, monstrous expansion, this runaway stretching of spacetime itself? The trigger of cosmic inflation remains one of the most tantalizing puzzles in all of physics. Picture a snowball perched at the top of a hill. Just a tiny nudge sends it tumbling, gathering speed until it's an unstoppable avalanche. The universe might have had its own version of that nudge, an unimaginably dense speck of spacetime poised on the edge of instability. One leading theory points to something called a scalar field, a kind of invisible energy blanket stretching across the early cosmos. Think of it like syrup spread over a pancake, thick and uniform. As this field's energy dropped, it could have released a colossal burst of repulsive gravity, shoving space apart faster than light. Another idea points to vacuum energy, the seething quantum froth that exists even in empty space. Under the extreme conditions of the newborn universe, this energy might have flipped a cosmic switch, kickstarting inflation's runaway expansion. Yet for all these theories, glaring gaps remain. Why did inflation start when it did? What made it stop so abruptly? These unanswered questions haunt physicists because that split second determined everything. The distribution of galaxies, the uniformity of the cosmic microwave background, even the very possibility of stars and planets forming. Without inflation's precise balance, the universe might have collapsed back on itself or torn apart too quickly for matter to clump together. The stakes couldn't be higher. If we ever uncover what set inflation in motion, we're not just solving a physics puzzle, we're peering into the rulebook of reality itself. The chaotic inflation model paints a vivid picture of those first explosive moments. Think of the early universe as a seething ocean of quantum foam, with random fluctuations creating pockets where inflation kicked off at different times and rates. In this scenario, our observable cosmos might just be one smooth patch in a far larger, wildly uneven landscape. It's like blowing up a balloon covered in bumps. Some areas stretch smoothly while others wrinkle or fold. This model suggests inflation wasn't a single, uniform event, but a chaotic dance of expanding regions, each with its own physics. Then there's the even more mind-bending idea of eternal inflation, a runaway process where the universe keeps spawning bubble universes endlessly. Picture a pot of water boiling vigorously with bubbles constantly forming, each one a self-contained cosmos with its own laws of physics. Our entire observable universe could just be one tiny bubble adrift in an infinite froth of others. Some of these bubbles might collapse instantly, while others could harbor entirely alien forms of matter or dimensions we can't even imagine. But here's where things get controversial. Can we ever really test these ideas? Some critics argue inflation has become too flexible, a theory that can explain almost any outcome by tweaking its parameters. It's like having a magic key that fits every lock. Without clear, observable predictions, how do we know if we're uncovering truth or just telling a compelling story? The cosmic microwave background offers clues like faint temperature variations that might be inflation's fingerprints, but even those are hotly debated. And then there's the multiverse problem. If eternal inflation is real and countless bubble universes exist beyond our own, does that make the theory untestable by definition? How do you prove something exists outside the boundaries of space and time as we understand them? These questions strike at the heart of what science can and can't explore. Yet, for all the controversy, inflation remains the best framework we have for explaining the universe's startling uniformity and vast scale. The hunt for evidence, whether in gravitational waves, rare particles, or deeper cosmic maps, is far from over. If inflation was this universe-stretching frenzy, why didn't it just keep going forever? That's the graceful exit problem, the mystery of how this breakneck expansion slammed on the brakes in less than a trillionth of a second. The answer lies in something physicists call reheating, and it's like the universe's ultimate reset button. Picture a roller coaster climbing to its peak, tension building with every inch. Inflation was that agonizing climb, space stretching tighter and thinner, energy building up like a coiled spring. Then, suddenly, the drop, the field-driving inflation, that cosmic syrup we talked about earlier, hit a critical point where its energy couldn't sustain the expansion anymore. It collapsed like a deflating balloon, dumping all that pent-up energy back into the fabric of space-time. This wasn't a gentle release, it was a firestorm. Space went from cold and empty to blisteringly hot in an instant. Particles erupted into existence, a seething soup of quarks, electrons, and radiation. Scientists call this moment reheating, but that word doesn't quite capture the violence of it. It was more like the universe struck a match in a room soaked with gasoline. Every corner of existence lit up with raw energy, setting the stage for the hot Big Bang we often think of as the beginning. Here's what's wild: without this transition, none of us would exist. If inflation hadn't ended precisely when it did, matter wouldn't have clumped into galaxies, stars would never have ignited, and the cosmic microwave background, that faint glow from the early universe, would look utterly different. The graceful exit had to be just right, or reality as we know it would have been impossible. Yet the details are still hazy. Did inflation end everywhere at once, or were there lagging patches where it sputtered out unevenly? Some theories suggest bubbles of space where inflation never stopped, hidden somewhere beyond our observable horizon. Others propose that quantum fluctuations left imprints during reheating, tiny wrinkles that eventually grew into the vast web of galaxies we see today. The search for answers isn't just academic. If we can pin down how reheating worked, we might finally understand why our universe looks the way it does, and whether other, wildly different universes could be lurking out there in the cosmic dark. Now zoom way in until you're staring at the universe when it was smaller than a proton. At this scale, nothing was truly still. Even in the vacuum of space, particles flickered in and out of existence thanks to quantum fluctuations. These weren't just microscopic hiccups, they were the seeds of everything we see today. When inflation hit, it didn't just stretch space, it magnified those quantum ripples like a cosmic projector, blowing them up to astronomical proportions. Imagine tossing a handful of pebbles into a pond, then suddenly stretching that pond to the size of an ocean. The tiny ripples become towering waves. That's what happened to those quantum jitters. Over billions of years, gravity tugged at the denser regions, pulling matter together until galaxies, clusters, and the vast cosmic web emerged from what was once subatomic static. The proof: look no further than the cosmic microwave background, the afterglow of the Big Bang. Satellite missions like Planck have mapped its faint temperature variations with astonishing precision, revealing patterns that match inflation's predictions almost perfectly. Warmer spots, those are the stretched-out quantum fluctuations where matter later clumped together. Cooler regions, the emptier stretches where less matter gathered. It's like finding baby pictures of the universe with its future structure already sketched in faint thermal ink. But here's where it gets eerie. Some of those CMB anomalies don't fit the standard model. There's a mysterious cold spot spanning billions of light years, too vast to explain with ordinary quantum noise. Could it be a collision with another bubble universe, a glitch in inflation's code, or is it a sign of physics we haven't discovered yet? The Planck data offers more questions than answers, but one thing's clear: those quantum fluctuations didn't just shape the cosmos, they left behind a forensic trail. And as we decode it, we're not just reading the universe's history, we're peering into the quantum rules that wrote it. There's a ghost haunting the early universe, a particle that should exist, but somehow we've never found a single trace of it. Meet the magnetic monopole, a bizarre theoretical relic that ought to be as common as stars, yet remains conspicuously absent. These aren't your everyday magnets with their familiar north and south poles. Monopoles are something far stranger: particles that carry just one magnetic charge, a north without a south, or vice versa. According to the laws of physics as we understand them, they should have been forged in abundance during the universe's earliest, hottest moments. So where did they all go? The answer might lie in cosmic inflation's exponential stretching. Picture a drop of dye in a glass of water. If you suddenly expanded that glass to the size of a swimming pool, the dye would become so diluted you'd barely detect it. That's what inflation could have done to monopoles. In the pre-inflation universe, they may have formed densely, like knots in a crumpled sheet. But as space ballooned at unimaginable speeds, those knots were stretched apart, scattered so thinly that today, you'd need to search a volume of space larger than our galaxy just to find one. Inflation didn't destroy monopoles, it hid them in the vastness, making their absence a silent clue that the theory might be right. But there's a twist. Some scientists argue that if inflation stretched monopoles beyond detection, it might have done the same to other exotic particles or even cosmic defects we haven't yet imagined. Could this explain other gaps in our understanding of the early universe? Or is the monopole mystery pointing us toward deeper flaws in particle physics itself? One thing's certain: their absence isn't just a curiosity, it's a cosmic breadcrumb, leading us back to the moment when the universe rewrote its own rules. The universe has a temperature problem, or rather, it should have one. Look in any direction, and the cosmic microwave background glows at almost exactly the same temperature, 2.725 degrees above absolute zero. That might not sound strange until you realize that some of these regions have been separated by billions of light years since the beginning of time. How could they possibly sync up? Think of 2 cups of coffee sitting on opposite ends of a football field. If they start at the same temperature but no heat can travel between them, they should gradually cool at different rates. Yet somehow, the universe's coffee stayed perfectly matched across distances so vast that light itself hasn't had enough time to travel between them since the Big Bang. This is the horizon problem, a glaring inconsistency that threatened to unravel cosmology itself. Enter cosmic inflation's brilliant fix. Before inflation, every corner of the observable universe was crammed into a space smaller than a marble where heat could easily spread evenly. Then, in a fraction of a second, inflation stretched that marble into a cosmos millions of times larger, locking that uniform temperature in place. It's like taking a snapshot of a well-mixed pancake batter, then zooming in until the image covers an entire city. The consistency remains flawless because the mixing happened before the expansion. But here's the clincher: without inflation, we'd see wild temperature variations in the cosmic microwave background, like splotches of uncooked batter in an otherwise smooth pancake. Instead, satellites show a near-perfect uniformity, with only the tiniest fluctuations precisely what inflation predicts, those minuscule variations. They're the quantum ripples we talked about earlier, stretched to cosmic scales and frozen in time when inflation ended, yet some scientists push back. Could there be other explanations? A few alternative theories suggest the universe might have simply started perfectly uniform, no inflation required. But that feels like cheating. It's the scientific equivalent of saying, it just was. Inflation doesn't just solve the horizon problem. It tells us how the universe pulled off this thermal balancing act, weaving the uniformity directly into the fabric of spacetime itself. The implications are staggering. If inflation hadn't smoothed things out, the cosmos would be a chaotic patchwork of scorching hot and icy cold zones, with galaxies forming only in isolated clusters. Life as we know it might never have had a chance. So when you look up at the night sky and see that serene, even darkness, you're actually glimpsing inflation's handiwork, a universe stitched together in perfect thermal harmony, all in the blink of an eye. The universe has a shape, or rather, it doesn't. That's the baffling truth behind the flatness problem, one of cosmology's most head-scratching puzzles. Imagine drawing a triangle on a sheet of paper. The angles add up to exactly 180 degrees because the paper is flat. Now try the same experiment on a globe. The angles bulge, adding up to more than 180 thanks to the curvature. For decades, scientists assumed the universe had some subtle bend, some cosmic curve to its fabric. But when they measured it using the cosmic microwave background as their ruler, they found something shocking. Space isn't just closed to flat, it's perfectly, eerily flat. Here's why that's impossible without inflation. Think of the early universe as a tiny, crumpled wad of paper. If you tried to smooth it out by stretching it gently, you'd still see wrinkles and folds. But if you blasted it with a cosmic hairdryer, inflating it exponentially in a fraction of a second, those creases would vanish. The paper would become so vast that any original curvature would be imperceptible, like trying to detect the bend of a single sheet across an entire football field. Inflation didn't just flatten the universe, it erased its curves so thoroughly that even today, our most precise instruments can't measure a single deviation. But there's a catch. Without inflation, the universe's density, the amount of matter and energy packed into space, would have had to be fine-tuned to an absurd degree from the very beginning. Like balancing a pencil on its tip for billions of years, the slightest imbalance would have sent reality spiraling into collapse or runaway expansion. Inflation solves this by literally stretching the problem away. It's not that the universe started perfectly balanced. It's that any initial wonkiness got diluted to nothingness by that explosive growth spurt. The implications are staggering. If the cosmos had even a 1% deviation from flatness at the Big Bang, today we'd either see space curling in on itself like a black hole or tearing apart into emptiness. Instead, we live in a Goldilocks universe where the geometry is just right, not too curved, not too warped, but exquisitely flat. And that's not just a lucky break. It's inflation's signature pressed into the fabric of reality like a cosmic fingerprint. So next time you look at the night sky, remember, you're not just staring into space. You're gazing at a flat, infinite canvas, one stretched smooth in the universe's first frantic heartbeat. The idea of a single universe might be far too small. If eternal inflation is real, then our cosmos could be just one bubble in an endless, frothing sea of universes, each with its own physics, its own dimensions, even its own version of time. Imagine a pot of water boiling violently, with bubbles forming, popping, and merging in a chaotic dance. Now scale that up to cosmic proportions. Each bubble is a self-contained universe, inflating from its own seed of spacetime, forever cut off from the others. We're not just talking about distant galaxies. Here we're talking about entirely separate realities, unreachable and unknowable, born from the same explosive process that shaped our existence. This isn't science fiction. String theory, one of the most ambitious frameworks in physics, suggests there could be as many as 10 to the 500 possible configurations for a universe, each defined by tiny differences in the way extra dimensions curl up or how fundamental forces balance. Inflation could be the engine that brings these possibilities to life, creating a sprawling multiverse where every conceivable set of physical laws plays out somewhere. Picture a cosmic lottery where the winning numbers determine whether atoms can form, whether stars shine, or whether life itself is possible. We just happen to live in a bubble where the numbers lined up in our favor. But here's where it gets thorny. If other universes are forever beyond our observational reach, how do we test this? Some scientists argue that collisions between bubble universes might leave scars, odd patterns in the cosmic microwave background like bruises on spacetime. Others look for subtle gravitational echoes, ripples from universes that brushed against ours before drifting away. So far, no smoking gun has been found, and critics argue that a theory that predicts everything might as well predict nothing. Yet the allure remains. The multiverse isn't just a wild speculation. It's a natural extension of inflation's runaway expansion, a consequence of physics pushed to its extremes. And if it's true, then the cosmic inflation era didn't just birth our universe. It set in motion an infinite cascade of realities, each one a separate experiment in the laws of physics. Our universe, with its perfect balance of forces, might be the rarest exception in a sea of failed attempts, or it might be utterly ordinary, one among countless others just like it. Either way, the multiverse forces us to confront a humbling thought. We may never be able to see beyond our bubble, but the universe or universes are far stranger than we ever imagined. The Big Bang singularity, the moment when all of space and time were crushed into an infinitely dense, infinitely hot point, has long been the ultimate cosmic cliffhanger. Conventional wisdom says inflation spared us from grappling with that mathematical nightmare by smoothing out the universe and giving it a clean starting line. But did it really? The Born-Guth-Vilenkin theorem, a landmark piece of mathematical physics, throws a wrench into that comforting idea. It proves that any universe undergoing average cosmic expansion, including ours, must have had a beginning. In other words, inflation might have reshaped the early universe, but it didn't erase the singularity. It just kicked the can down the road. Take a step back and think about what that means. If the theorem holds, then no matter how far you rewind the tape past inflation, past the reheating firestorm, past the formation of the first particles, you still hit a wall. A point where the equations of general relativity break down, where space and time lose all meaning. Inflation doesn't solve the singularity. It dresses it up in new clothes, leaving us with the same existential headache. What, if anything, came before? But not everyone agrees. Enter loop quantum cosmology, a radical alternative that rewrites the rules at the smallest scales. Picture spacetime not as a smooth continuum, but as a fabric woven from tiny, indivisible threads. In this framework, the universe doesn't collapse into a singularity, it rebounds. Like a ball bouncing off an unbreakable floor, the cosmos reaches a maximum density and then springs back outward, turning the Big Bang into a big bounce. No infinite densities, no mathematical meltdowns, just a cosmic reset button. The implications are staggering. If loop quantum cosmology is right, our universe might be one in an endless cycle of expansion and contraction, each phase leaving faint traces in the next. Gravitational waves from the pre-bounce era could still ripple through our cosmos, hiding in plain sight. The cosmic microwave background might bear scars from a previous universe's death throes. It's a vision that turns the singularity from a dead end into a gateway. Yet the debate is far from settled. critics argue that loop quantum cosmology's predictions are still too vague to test, while the Borde-Guth-Vilenkin theorem remains a formidable obstacle. The truth might lie somewhere in between, or in a theory we haven't even imagined yet. One thing's certain, the question of whether inflation truly escapes the singularity isn't just academic. It's a battle over the very nature of reality, and the answer could redefine our place in the cosmos. What if the force tearing our universe apart today is the same one that set it in motion at the dawn of time? Dark energy, that mysterious presence accelerating cosmic expansion, bears an uncanny resemblance to the repulsive gravity of inflation. Both seem to push space apart against all expectations, as if the vacuum itself holds some secret energy that defies gravity's pull. Could dark energy be inflation's leftover fingerprint, a fading echo of that primordial explosion? Think of it like a campfire dwindling to embers. Inflation's firestorm ended long ago, but perhaps its heat never fully dissipated. In quantum terms, fields don't just switch off, they settle into their lowest energy state. What we call dark energy might be that residual hum, the baseline energy of empty space that inflation left behind. The numbers don't quite line up, though. Inflation's energy was at least 10 to the 120 times stronger than today's dark energy. That's like comparing a supernova to a candle flame. Enter quintessence, a twist on the idea. Instead of a constant cosmological force, this theory proposes dark energy as a dynamic field slowly evolving over time, more like a dying vibration than a static relic. Picture a bell struck violently during inflation, its ringing fading over billions of years. Sometimes the tone dips, sometimes it surges. If quintessence is real, dark energy's strength might have varied across cosmic history, shaping the universe's expansion in ways we're only starting to measure. Yet contradictions linger. Inflation was a runaway process, while dark energy's effects emerged gently, dominating only after galaxies had formed. Some models suggest dark energy could be a new phase transition, an echo of inflation's reheating, but on a scale so slow it makes continental drift look instantaneous. Others speculate that multiple scalar fields existed in the early universe, with one driving inflation and another, subtler one lingering to become dark energy. The stakes: if these forces are linked, we might finally understand why the universe didn't just inflate and freeze. Instead, it gave rise to galaxies, then stars, then life, all while that ancient push still lingers, quietly steering cosmic fate. Decoding this connection could reveal more than dark energy's origin. It might rewrite the story of how everything, including us, came to be. The universe might be heading toward its most violent end, not with a slow fade, but with a catastrophic tear. Enter the Big Rip, a scenario darker than any black hole or heat death. Phantom energy, an extreme form of dark energy, could one day push cosmic expansion into overdrive, accelerating so fiercely that it shreds reality itself. Imagine a force so relentless that it doesn't just stretch space, it rips galaxies, stars, and even atoms apart in a final, apocalyptic crescendo. This isn't some distant hypothetical. If phantom energy's strength grows over time, unlike ordinary dark energy, which stays constant, it could trigger a new inflationary phase billions of years from now. Picture the early universe's explosive growth, but in reverse. Instead of space stretching smoothly, it fractures. First, galactic clusters would be wrenched apart, their gravity hopelessly outmatched. Then, individual galaxies would unravel, stars spiraling into the void. Eventually, even planetary systems would disintegrate, planets torn from their suns. The final moments, a nightmarish breakdown of spacetime itself. In the last fraction of a second, phantom energy's grip would overcome the very forces binding matter together. Atomic nuclei would split, protons and neutrons dissolving into quark soup. Even light would stretch into meaningless, infinite wavelengths, a silent scream swallowed by the void. Simulations of this scenario show space itself disintegrating like wet tissue paper, leaving behind utter nothingness. But here's where it gets eerie. Some theories suggest phantom energy isn't just a future threat. It might already be lurking in today's cosmic acceleration, subtly shifting the rules. If it exists, its fingerprints could hide in the way distant supernovae dim or how galaxy clusters slowly drift apart. The key lies in something called the equation of state, a number describing dark energy's push. If it dips below -1, phantom energy wins, and the Big Rip becomes inevitable. Yet not all hope is lost. Alternate models propose that phantom energy could decay or transition into something less destructive, like a field running out of steam. Others argue the Big Rip might be an illusion, a mathematical quirk rather than a physical certainty. But if the worst-case scenario proves true, it raises a chilling question. Did inflation sow the seeds of its own destruction? A force born in the universe's first moments might one day return to erase all traces of its existence. The irony is cosmic. The same mechanism that gave birth to galaxies could ultimately erase them, bookending the universe's story with symmetry, an explosive beginning and an even more violent end. The Big Rip isn't just a doomsday tale. It's a reminder that the universe's deepest mysteries are still shaping our fate, billions of years in the making. Deep in the cosmic shadows, there may lurk black holes unlike any we've seen, not born from collapsing stars, but forged in the furnace of inflation itself. These are primordial black holes, hypothetical remnants of the universe's most violent era, and they could be hiding in plain sight. Picture this: tiny, dense knots in the fabric of spacetime, formed when regions of ultra-dense matter collapsed under their own gravity during inflation's chaotic expansion. Some might be as light as a paperclip, others as massive as 1,000 suns. And here's the kicker: if they exist in vast numbers, they could solve one of cosmology's biggest puzzles, the mystery of dark matter. For decades, scientists have searched for dark matter particles underground, in space, and even at particle colliders. But what if the answer wasn't some exotic new particle at all? Primordial black holes could be lurking everywhere, invisible because they don't emit light, yet warping space around them with their gravity. They'd act like cosmic ghosts, bending starlight and tugging at galaxies in ways that perfectly mimic dark matter's effects. Some theories even suggest these black holes could congregate in halos around galaxies, or drift through the void as rogue gravitational anchors. But how do we find something that emits no light? The clues might lie in subtle cosmic disruptions. When a primordial black hole passes in front of a distant star, its gravity acts like a lens, briefly magnifying the star's light, a phenomenon called microlensing. Astronomers have scoured millions of stars for these fleeting flashes, but so far, the results are inconclusive. Another tantalizing possibility comes from gravitational waves. If two primordial black holes spiraled into each other, their collision would send ripples through spacetime detectable by observatories like LIGO. A few of the black hole mergers we've already spotted might not be stellar remnants at all, but ancient relics from inflation itself. Yet the plot thickens. If primordial black holes are dark matter, why haven't we seen more of them? Their absence could mean they're too small, too diffuse, or simply not there. Or perhaps they're hiding in mass ranges we haven't probed yet. The hunt is far from over, and the stakes couldn't be higher. If even a fraction of dark matter turns out to be primordial black holes, it would rewrite our understanding of both the early universe and the invisible scaffolding holding galaxies together. Now, shift your gaze to another cosmic whisper from the inflation era: gravitational waves. Not the ones from black hole collisions we detect today, but primordial gravitational waves. The vibrations sent rippling through spacetime when inflation's exponential expansion jolted the universe. These waves would carry a unique signature, a telltale imprint of that explosive moment. Detecting them would be like finding a recording of the Big Bang itself. The challenge: these waves are ancient and faint, stretched to near invisibility by billions of years of cosmic expansion. But hope lies with missions like LISA, the Laser Interferometer Space Antenna, set to launch in the 2030s. Unlike ground-based detectors, LISA will float in space, free from Earth's vibrations, with lasers precise enough to measure shifts smaller than an atom across millions of miles. It's the ultimate cosmic stethoscope, tuned to listen for the faint heartbeat of the early universe. The prize: a smoking gun for cosmic inflation. Primordial gravitational waves would leave a distinctive curl in the polarization of the cosmic microwave background, a pattern nicknamed B modes. Finding this signal would confirm inflation's wildest predictions, proving that spacetime itself once stretched faster than light. It might even reveal details about the scalar field that powered inflation. Was it a single, smooth force or a chaotic interplay of multiple fields? But here's the catch: so far, definitive evidence has eluded us. Initial claims of B-mode detection in 2014 turned out to be cosmic dust masquerading as a signal. The search continues, with ever more sensitive experiments scanning the skies for that elusive twist in the universe's oldest light. The connection between primordial black holes and gravitational waves isn't just academic. Both are cosmic breadcrumbs leading us back to inflation's fingerprints. One offers a solution to dark matter, the other proof of the universe's explosive birth. Together, they paint a picture of a cosmos far stranger and more dynamic than we ever imagined, a place where black holes might lurk unseen, and spacetime still hums with echoes of its first unimaginable moments. The cosmic microwave background should be a nearly perfect snapshot of the early universe, a uniform glow with only the faintest wrinkles. But then there's the cold spot. A sprawling region over 1 billion light-years wide, chillingly colder than its surroundings by a few millionths of a degree. At first glance, it seems insignificant. But statistically, it shouldn't exist. This anomaly defies inflation's predictions of a smoothly distributed cosmos, and scientists are locked in a debate over whether it's a cosmic hiccup or a crack in our understanding of reality. One camp argues the cold spot is just a supervoid, an enormous, mostly empty bubble in space where matter is unusually sparse. Picture diving into a pool and hitting a pocket of lukewarm water. As light travels through such a void, it loses energy, shifting to longer, colder wavelengths, an effect called the integrated Sachs-Wolf effect. But here's the problem: simulations show voids this large are vanishingly rare. For the cold spot to be a random fluctuation would be like rolling a dice 1,000 times and getting only sixes. Possible, technically; likely, hardly. That's where the exotic explanations come in. Some theorists propose the cold spot could be a scar from a cosmic defect, a frozen-in flaw in spacetime's structure left over from the universe's hyperactive infancy. Think of it like a crack in ice forming as water freezes. During inflation, certain phase transitions might have spawned bizarre structures, domain walls, textures, or even cosmic strings, one-dimensional wrinkles in spacetime with the mass of a galaxy compressed into a thread thinner than an atom. If one of these defects passed through our cosmic neighborhood, its gravitational tug could have warped the CMB, leaving behind a cold fingerprint. But the wildest idea: that the cold spot isn't from our universe at all. If inflation spawned a multiverse, this anomaly could be a bruise from a collision with another bubble universe, a gravitational handshake from a reality with entirely different physics. It's a fringe theory, but one that's shockingly hard to rule out. The truth is, we're still gathering clues. Future galaxy surveys might confirm the supervoid's existence, while next-generation telescopes could hunt for the twisted spacetime signatures of cosmic defects. Until then, the cold spot remains a tantalizing enigma, a reminder that even our best cosmic maps might still be missing something fundamental. And if history's any guide, it's often the anomalies that lead us to the next revolution in understanding. Astronomers are locked in a standoff over one of the most basic numbers in cosmology, just how fast the universe is expanding right now. It's called the Hubble constant, and the latest measurements are refusing to agree. On one side, we have observations of nearby galaxies and supernova, pointing to an expansion rate around 73 kilometers per second per megaparsec. On the other, the cosmic microwave background, our snapshot of the infant universe, suggests a slower pace, closer to 67. At first glance, the difference seems small, but statistically, it's a glaring mismatch. If both measurements are correct, we're missing something fundamental about how the cosmos works, and that something might trace all the way back to inflation's first split-second frenzy. Here's where things get intriguing. Inflation didn't just stretch space, it set the initial conditions for everything that followed, including how fast galaxies would eventually drift apart. Theorists have long assumed the universe's expansion rate would gradually slow down thanks to gravity's relentless pull. But dark energy threw a wrench into that, accelerating the expansion billions of years later. The Hubble tension could be a hint that dark energy isn't the only twist, that something else, something unexpected, happened in between. Maybe inflation didn't wind down as smoothly as we thought, leaving behind ripples in spacetime that subtly nudged the expansion rate off course. One radical idea, a brief resurgence of inflation-like expansion long after the cosmic dawn, a dark inflation phase triggered by an unknown field or phase transition. Imagine hitting the gas pedal twice during a road trip, once at the start, then again halfway through. The second burst wouldn't need to be as violent as the first, just enough to tweak the universe's speedometer. Alternatively, there could be hidden particles from the early universe, sterile neutrinos or other exotic relics, still influencing gravity's tug-of-war today. But critics push back. Could the tension just be measurement errors? Telescopes studying nearby galaxies rely on a cosmic distance ladder, each rung introducing potential inaccuracies. The CMB, meanwhile, requires assumptions about the universe's composition. If we've underestimated dust obscuring supernova or miscalculated dark matter's clumpiness, the discrepancy might vanish. Yet after decades of refining tools, the gap stubbornly persists, fueling suspicion that we're glimpsing the edges of known physics. This isn't just academic quibbling. If the Hubble tension demands new physics, it could reshape our understanding of dark energy, neutrinos, or even the scalar fields that drove inflation. The stakes, a universe more unpredictable and more fascinating than we ever imagined. Whether it's unseen particles, phantom forces, or echoes of inflation's last gasp, one thing's clear: the cosmos is still hiding rules we haven't yet decoded. And that's the most exciting kind of mystery there is. What if the universe didn't have a beginning at all? No fiery singularity, no moment of creation, just an elegant cosmic curve where time itself loses its edge. That's the radical heart of the Hawking-Hartle no-boundary proposal, a quantum twist on origins that reimagines the Big Bang not as a starting gun, but as a smooth transition from nothingness. Picture the entire history of the cosmos as a globe, not a sphere in space, but a four-dimensional shape where time behaves like latitude. At the North Pole, you'd expect a sharp point marking t=0, the instant of creation. But Hawking and Hartle's math flattens that point into something subtler, like the rounded tip of a pear. Here, the chaotic frenzy of the early universe blends seamlessly with imaginary time, a mathematical trick where time acts like another dimension of space. In this quantum fog, asking what came before the Big Bang becomes as meaningless as asking what's north of the North Pole. Animations of this model are mesmerizing. They show spacetime not as an exploding fireworks shell, but as a gentle warp settling into expansion, like watching a pond's surface smooth after a pebble's ripple. Quantum fluctuations, those tiny jitters in the fabric of reality, bubble up naturally from this curved geometry, seeding galaxies without the need for a cataclysmic starting point. It's a universe that doesn't begin as much as it emerges, a cosmic phoenix born from its own ashes without ever truly dying first. But here's where it gets even stranger. The no-boundary proposal doesn't just eliminate the singularity, it suggests the universe could have spontaneously created itself from nothing. Not empty space, but literal nothingness. How? Through a quantum loophole where the total energy of the cosmos remains zero. Matter and energy on one side of the ledger, gravity's negative curvature on the other, perfectly balanced. It's the ultimate free lunch, a reality bootstrapping itself into existence because on quantum scales, impossible is just another word for improbable. Critics pounce on the theory's murky testability. Without a traditional beginning, how do we look for proof? Supporters point to subtle signatures in the cosmic microwave background, specific patterns in polarization or temperature variations that might betray this curved origin. Others suggest the universe's overall geometry holds clues. If space isn't just flat but slightly closed, like the surface of a vast, invisible sphere, it could hint at the no-boundary conditions' influence. Yet the proposal's real power lies in its audacity. It doesn't just tweak our origin story, it rewrites the language of beginnings altogether. Time becomes a property that unfolds rather than starts, and the Big Bang transforms from a wall at the edge of understanding into a bridge between existence and the quantum unknown. Whether the theory holds up or not, it forces us to confront a humbling truth. The universe might not need a first cause to exist. It might simply be a timeless, self-contained reality where the question of origins dissolves into the beautiful, baffling math of the cosmos itself. Could the universe's explosive birth have erased its own memory? The cosmic inflation era might hold a disturbing secret, one that echoes the infamous black hole information paradox. When a black hole devours matter, it appears to destroy information about the objects it consumes, violating a sacred rule of quantum mechanics. Information must never be lost. Inflation could be committing the same crime on a cosmic scale. During those first chaotic moments, quantum fluctuations, tiny ripples in the fabric of space-time, were blown up to astronomical proportions. These ripples became the seeds of galaxies, stars, and planets. But here's the catch: the universe stretched so violently that some regions were pushed beyond our cosmic horizon, forever out of reach. The information stored in those patches didn't just become inaccessible, it was effectively erased from our observable universe. It's like shredding a document and scattering the pieces into a hurricane. The words might still exist, but you'll never piece them back together. This isn't just theory. The holographic principle, born from black hole physics, suggests all the information in a region of space might be encoded on its boundary, like a cosmic DVD where the surface holds the data for the entire three-dimensional movie. If true, then inflation's exponential expansion could have scrambled that encoding beyond recovery, leaving us with a universe where vast amounts of quantum data are permanently missing. But there's a twist. Some physicists argue inflation doesn't destroy information. It just hides it in correlations too complex to decode. Like mixing two colors of paint until they appear uniform, the original hues still exist in the blend, even if we can't separate them. Others propose that lost information might still be recoverable through gravitational waves or quantum entanglement, subtle threads stitching the cosmos together in ways we're only beginning to understand. The stakes couldn't be higher. If inflation truly obliterates quantum information, it challenges our deepest beliefs about how reality operates. But if the data is merely hidden, waiting for us to crack the cosmic cipher, then the universe might still play by quantum rules, just on a scale so vast we haven't learned to read them yet. This paradox isn't just about the past, it's a window into whether the universe forgets or simply remembers in ways we can't yet comprehend. The universe seems suspiciously well-tailored for life, a cosmic jackpot where every dial was set just right. If inflation had lasted a fraction longer, space would have stretched so thin that matter could never clump into galaxies. A fraction shorter, and the cosmos might have collapsed back on itself before stars could ignite. Even tiny tweaks to inflation's energy or expansion rate would have left reality barren, empty, or wildly unstable. So how did we get so lucky? One answer makes scientists squirm: the anthropic principle. It's the idea that the universe must look life-friendly because we're here to observe it. Imagine winning a lottery and asking, what were the odds? Well, if you hadn't won, you wouldn't be around to ask. Similarly, countless universes might exist with different physics, but only in the rare Goldilocks zones, where constants align just right, can life arise and ponder its own existence. It's less about luck and more about a cosmic selection bias. We're here because here is the only place we could be, but the multiverse takes this further. If inflation spawned countless bubble universes, each with random physical laws, then statistically, a few would hit the life-permitting jackpot. Think of it like a vast cosmic casino where most universes are losing tickets, too cold, too chaotic, or too short-lived. Our universe isn't special, it's just the one where the slots happen to line up. Critics argue this explanation feels like a cop-out, a way to dodge the deeper question of why these precise conditions exist. Some theorists hunt for fundamental laws that require life-friendly parameters, weaving them into the fabric of reality itself. Others propose that the universe's fine-tuning isn't accidental but inevitable, a consequence of physics we haven't yet uncovered. The debate cuts to the core of science itself. Is our universe a fluke in a chaotic multiverse, or does its perfection point to deeper, undiscovered symmetries? Either way, the lucky universe problem isn't just about our origins. It's about whether reality is a cosmic accident or a puzzle waiting to be solved. What if the universe didn't begin with a bang, but with a bounce? Enter the cyclic universe model, a radical reimagining of cosmic origins where the Big Bang isn't a starting point but a reset. In this view, our universe is just the latest chapter in an endless cycle of expansion, collapse, and rebirth, each iteration stretching and smoothing space-time like dough kneaded between cosmic hands. At first glance, it sounds like inflation's rival. Both theories explain the universe's eerie uniformity, but where inflation relies on a one-time superstretch, cyclic cosmology argues that endless repetition over countless eons could have ironed out the cosmos' wrinkles naturally. Sir Roger Penrose's version, called conformal cyclic cosmology, takes this even further. Picture the far future of our universe where black holes have evaporated, particles have decayed, and space is an endless, lifeless void. In Penrose's framework, this bleak expanse isn't the end, it's the bridge to a new beginning. As the universe expands to infinity, its geometry becomes indistinguishable from the infinitesimal singularity of a new Big Bang. Time loses meaning, scales blur, and the cosmos undergoes a conformal rescaling, a mathematical trick where infinite stretch meets infinite shrink, sewing the last moments of one eon seamlessly into the first moments of the next. Here's the twist: these eons aren't perfect copies. Each cycle inherits faint imprints from its predecessor, like echoes in a cosmic canyon. Penrose claims to have spotted these echoes in the cosmic microwave background, concentric rings of anomalous temperature variations he calls Hawking points, remnants of supermassive black hole collisions from past eons. If real, they'd be ghostly fingerprints of universes long gone, etched into the sky. Critics argue these patterns could be statistical flukes, but the mere possibility forces us to reconsider everything. The clash with inflation is stark. Where inflation solves uniformity with a single, violent expansion, cyclic cosmology spreads the work over eternity. Imagine polishing a rough stone. Inflation is like sandblasting it smooth in seconds, while cyclic cosmology lets endless tides wear it down gradually. Both reach the same destination, but by wildly different paths, yet the cyclic model faces its own hurdles. How does an infinitely stretched universe bounce into a new one without violating energy conservation? Penrose's answer lies in the conformal rescaling, a reset where all particles lose mass and the universe forgets its size, allowing infinity to become zero. It's a breathtaking idea, but one that hinges on untested physics. Meanwhile, inflation's predictions about the cosmic microwave background have held up remarkably well, even if the theory remains frustratingly flexible. The debate isn't just academic. If Penrose is right, our universe is a phoenix in an endless cycle of death and rebirth, carrying scars from its past lives. If inflation holds, we're the fleeting product of a singular, unrepeatable explosion. Both force us to confront the same haunting question: is our cosmos a one-time marvel or just one page in an infinite cosmic storybook? The answer might lie in the whispers of ancient black holes or in the faintest ripples of space-time waiting for us to listen. In the frantic first moments of inflation, the universe didn't just explode, it lingered. The energy field driving this runaway expansion didn't vanish instantly. Instead, it decayed with a slowness that defies intuition, like a supercharged engine cooling to a whisper over what felt like an eternity in a trillionth of a second. This slow roll phase is one of inflation's most puzzling quirks. Why didn't the field collapse immediately, and how did it sustain just enough push to stretch the cosmos so perfectly? The answer might lie in something surprisingly familiar: the Higgs field. Picture a marble rolling down a shallow, almost flat hill. The steeper the slope, the faster it drops. Inflation's energy field behaved like that marble, but on a cosmic scale. For reasons we're still untangling, the slope of its potential energy was absurdly gentle, allowing the field to lose energy gradually rather than crashing down. This slow roll was crucial. Too steep, and inflation would have ended too abruptly, leaving the universe lumpy and uneven. Too flat, and space might still be stretching today, devoid of galaxies or stars. The Higgs field, the same one that gives particles mass, offers a clue. Like inflation's field, it's a scalar field with a Mexican hat potential energy shape, where particles gain mass by settling into the hat's brim. Some theorists suspect inflation's field might have operated on a similar principle, just at energies trillions of times higher. Here's where things get speculative. Supersymmetry, or SUSY, a beloved but still unproven theory, could bridge the gap. SUSY predicts a zoo of undiscovered particles, each with a heavier superpartner. If these partners existed in the early universe, they might have subtly altered the slope of inflation's energy field, acting like speed bumps to stretch out its decay. It's a tantalizing link between the infinitesimally small and the cosmically vast, one that could explain why inflation's slowdown was so exquisitely tuned. Yet the slow roll mystery isn't just about energy fields, it's about timing. That delicate balance between rapid expansion and gradual decay had to be just right to leave behind a universe with the smoothness we observe today. Simulations show that even minor tweaks to the roll speed would produce a cosmos either too chaotic or too empty for life. It's as if the universe's recipe called for a pinch of patience, a pause in the chaos that let everything else fall into place. The deeper we dig, the more questions arise. Did the slow roll happen uniformly everywhere, or were there patches where inflation ended earlier, leaving behind pockets of higher density? Could these variations explain some of the anomalies in the cosmic microwave background? And if SUSY is real, could its particles leave fingerprints not just in particle colliders, but in the large-scale structure of spacetime itself? The slow roll might seem like a minor detail in inflation's grand drama, but it's the key to understanding why our universe looks the way it does, and whether its flawless expansion was a one-time fluke or the hint of a deeper, hidden symmetry. What if the question, what came before inflation, is fundamentally flawed? Some physicists argue that time itself might be an illusion at the deepest levels, that the concept of before loses all meaning when we peer past the veil of the Big Bang. Sean Carroll and Jennifer Chen's groundbreaking work paints a picture where inflation isn't the beginning, but merely a transition point in an eternal, self-sustaining cosmos. Their model suggests the universe didn't arise from nothing. It emerged from an endless sea of quantum fluctuations where time doesn't flow in any particular direction and causality loops back on itself like an Ouroboros. Picture a bubbling pot of water where quantum foam constantly generates tiny bubbles of space-time. Most collapse instantly, but a rare few, like our universe, inflate into full-fledged realities. In this view, inflation wasn't a one-time event. It's part of an infinite cycle where universes sprout from the quantum vacuum like mushrooms after rain, each with its own arrow of time pointing away from its local Big Bang. The kicker: there's no ultimate beginning, just an eternal now where past and future are illusions of perspective. Yet this clashes starkly with theological interpretations that have grappled with first causes for millennia. The ancient concept of creatio ex nihilo, creation from nothing, resonates across religions, from the biblical "let there be light" to Hindu scriptures describing cyclical universes arising from Vishnu's dream. Some modern theologians argue quantum models merely push the problem back a step. If quantum fluctuations birth universes, what birthed the quantum laws enabling those fluctuations? The debate hinges on whether reality requires an uncaused cause, or if the question itself stems from our limited, time-bound perception. Critics of Carroll and Chen's model point out it still relies on pre-existing quantum fields, a sort of cosmic stage waiting for its actors. Others counter that even those fields might be emergent properties of deeper mathematics, rendering before as meaningless as asking what's north of the North Pole. Meanwhile, certain multiverse theories propose inflation wasn't the first chapter, but a middle act in an even grander story, a branching point in a pre-existing quantum landscape. The tension highlights a profound divide. Does the universe owe its existence to timeless physics, or does it point toward something transcendent? Perhaps the answer lies beyond human frameworks altogether. After all, our brains evolved to track cause and effect in a three-dimensional world, not to comprehend the birth of spacetime itself. Whether the first cause dilemma reveals deep truths about reality or merely the limits of our imagination remains one of cosmology's most humbling mysteries. The only certainty: the deeper we dig, the more the universe resists simple origin stories. String theory throws open a door to dimensions beyond our own, a hidden landscape where the fabric of reality isn't just three-dimensional space, but a vast, vibrating tapestry of higher-dimensional membranes, or brains for short. Picture these brains as invisible sheets floating in a multidimensional cosmos, each one potentially hosting its own universe with unique physics. Now imagine two of these colossal membranes drifting through the void until they collide. That cataclysmic smash might not just have sparked our universe, it could be the secret engine behind cosmic inflation itself. This is brain inflation, a theory that trades the abstract scalar fields of traditional inflation models for something even wilder: the violent tango of higher dimensional objects. When brains collide, the energy released could have ignited inflation's exponential expansion, like striking a match in a cosmic fuel depot. The math suggests these collisions wouldn't just create a one-time burst, they'd generate ripples across the brain's surface, warping spacetime in ways that perfectly mimic the repulsive gravity of classic inflation. It's as if the universe didn't just inflate from within, but was pushed into being by forces from another dimension. The evidence might lie in gravitational waves. Brain collisions wouldn't be gentle, they'd send shockwaves through the higher dimensional bulk, vibrations that could imprint onto our universe as primordial gravitational waves. Future detectors like LISA might catch these echoes, revealing not just how inflation started, but that our cosmos is one page in a multidimensional storybook. Even more tantalizing, if brains sparked inflation, they might have left behind cosmic strings, one-dimensional scars in space-time, thinner than an atom but stretching across the universe. These bizarre relics could warp light from distant galaxies or emit faint gravitational hums, offering clues to their existence, but the implications go deeper. If our universe lives on a brain, there could be others parallel worlds separated by less than a millimeter in a higher dimension, yet utterly invisible to us. Some theories suggest these neighboring brains might even bump into each other again, triggering new inflationary phases. It's a dizzying vision, inflation not as a one-time event, but a recurring drama in a cosmos far vaster than we ever imagined. Critics argue that brain inflation trades one mystery for another, swapping the scalar field's origins for the unexplained existence of brains themselves. Yet for all its audacity, the theory bridges two titanic ideas: inflation's explosive growth and string theory's hidden dimensions. Whether it holds up or not, it forces us to confront a humbling possibility. The birth of our universe might not have been a solitary act. It could have been a collision, a moment of cosmic contact we're only now learning to see. The holographic principle turns everything we think we know about reality inside out literally. What if the three-dimensional universe we experience is just a projection, like a movie playing on the surface of an enormous cosmic bubble? This isn't science fiction, it's a serious theory rooted in black hole physics and string theory, with bizarre implications for cosmic inflation. To understand how this works, picture a black hole. According to groundbreaking work by physicists like Jacob Bekenstein and Stephen Hawking, all the information about objects swallowed by a black hole isn't lost. It's somehow encoded on its two-dimensional event horizon, the boundary where nothing can escape. The three-dimensional details of a collapsing star are mysteriously preserved on this flat surface, like a hologram storing depth on a flat sticker. The AD/S/CFT correspondence, a mathematical framework developed by Juan Maldacena, takes this idea even further. It proposes that a higher dimensional universe like ours could be perfectly described by a lower dimensional theory operating on its boundary. In other words, our sprawling 3D cosmos might just be the shadow of a 2D reality we can't see. Now tie this back to inflation. During that explosive expansion, the universe stretched so rapidly that quantum fluctuations were blown up to cosmic scales, creating the seeds for galaxies. But here's the twist: if the holographic principle holds, those fluctuations weren't just random jitters in 3D space. They were projections of data encoded on a distant 2D surface, like pixels on a screen rendering the universe's grand tapestry. Inflation didn't just expand space, it magnified a cosmic hologram, stretching the pixels until they became the galaxies we see today. The implications are staggering. If true, it means the universe's entire history, every star, every planet, even the thoughts in your brain, could be nothing more than a complex pattern vibrating on some unimaginably vast boundary. It's as if reality is a game of cosmic charades, with the real action happening in a dimension we'll never perceive. Critics argue the math is still speculative, and linking this directly to inflation remains controversial. But if future experiments like precise measurements of gravitational waves or quantum entanglement in space find evidence of holographic encoding, it could redefine not just how we see the universe's birth, but the very nature of existence itself. The holographic universe isn't just a theory about space. It's a challenge to reality as we know it, one where the boundaries of perception might be the only thing keeping us from seeing the truth. Somewhere in the infinite expanse spawned by cosmic inflation, there might exist a naked brain, a self-aware entity that flickered into existence purely by chance, complete with false memories of a past that never was. This unsettling thought experiment is called the Boltzmann brain paradox, and it forces us to confront a bizarre consequence of an eternal, inflating universe. If space stretches endlessly and quantum fluctuations can produce anything given enough time, from atoms to galaxies, why not conscious minds? The paradox traces back to 19th century physicist Ludwig Boltzmann, who grappled with how orderly systems emerge from chaos. His insight: given enough time, even random molecular motion will briefly arrange itself into unlikely patterns, like a tornado assembling a jet engine from scrap metal. Apply that to an infinite cosmos and the statistics get terrifying. In a universe old and vast enough, quantum randomness could assemble a fully functioning brain, complete with fabricated sensory input, convinced it's living a normal human life. And if the cosmos is truly infinite, Boltzmann brains would outnumber real, biologically evolved minds by an unimaginable margin. Inflation cranks this nightmare to 11. If eternal inflation spawns endless bubble universes, each with its own physical laws, the probability of Boltzmann observers existing somewhere skyrockets. Worse, some regions of spacetime might be so hostile to life that fleeting quantum-generated consciousness becomes the only observers around. The kicker: you can't prove you're not one. That memory of eating breakfast could be a statistical fluke. The stars above might be synthetic sensory noise, the universe itself potentially an elaborate illusion conjured by a lone brain that formed and dissolved in the void. But physicists push back. Reality seems too stable, too consistent to be the hallucination of a momentary fluctuation. Boltzmann brains should glitch constantly, laws of physics shifting, memories rewriting, yet our world holds firm. This suggests the paradox might hint at deeper truths. Either inflation isn't truly eternal, cutting off the time needed for freak observers to arise, or there's a fundamental mechanism preventing such aberrations. Some theorists point to quantum decoherence, the idea that complex, self-aware structures require stable interactions with their environment, something a Boltzmann brain, adrift in emptiness, couldn't maintain. The debate touches the limits of science itself. If we accept that anything possible must happen given infinite time and space, how do we trust our observations? Cosmologists counter with the principle of mediocrity, the idea that we're likely typical observers, not extreme statistical outliers. After all, real galaxies and planets vastly outnumber random brain fluctuations in terms of entropy cost. But in an infinite multiverse, can we ever be sure? Perhaps the ultimate lesson is humility. The Boltzmann brain paradox doesn't just question reality, it forces us to ask what reality even means. If consciousness can emerge from chaos, does it matter whether its origins lie in biology or quantum accident? The answer might lie not in physics, but in philosophy's oldest puzzle: how to distinguish illusion from truth when all we have is our own uncertain mind. The universe might have two possible endings, one slow and silent, the other sudden and violent, and the key to both lies hidden in inflation's abrupt finale. On one hand, we have the Big Freeze, a fate so gradual it makes glaciers look impatient. Over trillions of years, galaxies will drift apart like lonely ships in an ever-widening sea, their stars burning out one by one until the cosmos is a graveyard of dead matter and fading radiation. Space itself will stretch thinner and colder, expanding until the last black hole evaporates into nothingness, leaving behind only a dilute soup of particles too far apart to ever interact again. This is entropy's victory, a universe that doesn't so much end as forget itself, fading into a darkness so complete it might as well be infinite. Yet there's a far more explosive alternative: vacuum decay, where the very fabric of reality self-destructs in a chain reaction faster than light. Imagine the universe as a fragile bubble resting on a knife's edge. Inflation's end left space in what we call a false vacuum, a seemingly stable state that's actually metastable, like a pencil balanced on its tip. Quantum mechanics says that given enough time, a tiny region of space could randomly tunnel into a truer, lower energy vacuum. If this happens, a sphere of destruction would bloom outward at light speed, rewriting the laws of physics as it expands. Inside this sphere, atoms disintegrate, forces unravel, and space-time itself reconfigures into something unrecognizable. One moment, you're sipping coffee. The next, you and the coffee cease to exist as you knew them, erased by a wall of annihilation you'd never see coming. The chilling part, vacuum decay, could already be underway somewhere beyond our cosmic horizon. Inflation's mechanism suggests that if one patch of space collapses into this true vacuum, the bubble's expansion is unstoppable, a cosmic contagion. Some theories even suggest that inflation's own end was triggered by a similar phase transition, meaning our universe might just be a temporary eddy in a larger, more unstable ocean. The stakes couldn't be higher. If the big freeze is our fate, the universe dies with a whimper, a drawn-out sigh of equilibrium. But vacuum decay, that's a scream in the dark, a total reset button. The eerie parallel between inflation's fiery birth and this potential demise isn't lost on physicists. Both involve phase transitions, both reshape reality in an instant. One gave us everything, the other could take it all away. Here's the twist: we might already see clues in the cosmic microwave background. Subtle anomalies in its polarization could hint at vacuum instability, like hairline cracks in a dam. Particle colliders are hunting too. If the Higgs boson's mass is just slightly lighter than predicted, it could place us perilously close to the edge. The numbers are terrifyingly fine-tuned. A 1% shift in certain constants might doom the universe to eventual decay, while a different 1% could secure its longevity. So which will it be, the slow unraveling or the quantum lightning strike? The answer might depend on inflation's most elusive details, the exact shape of the scalar field's potential, the energy left behind after reheating, or even whether dark energy evolves over time. It's a cosmic coin toss, and the odds are written in math we're still deciphering. But one thing's certain, the same physics that birthed the stars may have already signed their death warrant. The universe's beginning and end might be two sides of the same equation, a reminder that creation and destruction are never truly separate, just moments in a story far larger than us. From the violent trigger that set off cosmic inflation to the bizarre paradox of Boltzmann brains floating in the void, we've journeyed through 25 of the universe's strangest enigmas. Think back, a newborn cosmos smaller than an atom, stretching faster than light, the eerie flatness of space so perfect it defies probability, the missing magnetic monopoles, phantom relics of a time when reality played by different rules. The haunting cold spot in the cosmic microwave background, a possible bruise from a collision with another universe, the Higgs field's delicate dance, slowing inflation just enough to let galaxies form. The holographic principle, suggesting our 3D reality might be a shadow cast from a distant 2D edge. And of course, the ultimate question, did time itself have a beginning, or are we caught in an endless cycle of cosmic rebirth? Each mystery peels back another layer, revealing how little we truly understand about the universe's first moments. Was inflation a one-time event, or does it still lurk in the void, waiting to tear reality apart? Are we alone in this cosmos, or is our universe just one bubble in an infinite multiverse? The answers could rewrite not just physics, but philosophy itself. Now it's your turn. Which of these cosmic puzzles keeps you up at night? The phantom energy that might one day shred the universe, the primordial black holes that could be hiding in the dark, silently shaping galaxies, or the terrifying possibility that you and everything you know might just be a fleeting fluctuation in an endless sea of nothingness. Drop your thoughts in the comments below, and let's keep the conversation going. And stay tuned, because in our next deep dive, we'll explore the boldest theories scientists have proposed to solve these mysteries. From quantum loops to colliding brains, the hunt for answers is far from over. The universe's greatest story is still being written, and you've got a front row seat. So keep looking up. The cosmos isn't done surprising us yet.